In this video, we're going to look at how to calculate a one-way ANOVA in a spreadsheet without having to rely on any kind of extensions or added in data analysis tools. We're just going to create a standard kind of calculator technique in our spreadsheet that will allow us to answer these types of questions repeatedly. So here's a typical ANOVA question where we have three groups with measurements, and we're just going to ask the question, does the average of one of these groups differ from the others? So in this scenario, we have a hospital that wants to determine if the type of treatment that a patient receives for pneumonia is a factor in their recovery time. And the table of data that we have is the number of days it took for a bunch of randomly selected patients to recover from pneumonia, given the three different treatments, right? Either they spent a few hours in the hospital, I don't know, receiving fluids or whatever, or they had to have an overnight stay in the hospital, or they just, gave them some medication and sent them home. Those are the three groups. Now you'll notice a couple things. First and foremost, our three groups do not have the same sample size. That is not necessary when conducting an ANOVA. You can have different sample sizes for the three samples. The other thing that we obviously have is some sort of measurement, or in this case, a count, because we're counting up how many days it took until they recovered. So we have quantitative data, so we can calculate means of each of those three groups. The null hypothesis is always that all of the means are the same. And then the alternative hypothesis is always that one of them is different, or at least one of them is different. So the way this one is worded is it says at least two of the means differ from each other. That's just another way of saying they can't all be the same, right? If one of them differs, it differs from one other, at least one other, mean. So that's the idea. It's kind of a stupid way to say it because you can't have at least two means that differ from each other. If one average was 5, the other average was 5, and then the last average was finally 7, which is different, it differs from both the first group and the second group. So technically there's three groups that differ, right? So anyhow, it's a weird thing. The wording is a little strange, but basically we're just saying they can't all be the same. Now, that doesn't mean they all have to be 5. They just, we're looking for, do they differ significantly, right? Statistics is all about a significant difference. So, you could have a 5, a 5.1, and a 5.2, and they would still be close enough kind of thing. But this is what the ANOVA test is going to tell us, is how significant are those differences, and we're going to get a p-value like we do for, all of these hypothesis tests, and then we're going to compare that p-value to some alpha level that we set. And in this case, we're setting alpha at 1%. But remember, as the researcher, you can set alpha to whatever you want. The standard seems to be 5%, but in this case, we're going to try 1%. Okay, so this is our scenario. To tackle an ANOVA, the first thing you have to do is copy your data and put it into your spreadsheet. So you're going to highlight the table, do Control-C, and then Control-V into your spreadsheet, or if you're in a Mac, I think it's Option-C and Option-V or something along those lines, but you get the idea. Get your data into your spreadsheet, and here is my data in my spreadsheet. And then you're going to need to set up some spaces to calculate some things. You're going to need a column to make some calculations of some deviation scores. We're just going to call them squares because we're going to take squared deviation scores. It's going to look and feel a lot like when we calculated standard deviation kind of by hand in a spreadsheet in a previous lesson. We're going to need a place over here where we're going to house a bunch of statistics that we're going to calculate on all three groups. And then we have one spot here. So over here, we're going to let our spreadsheet calculate things for us. The cell that has a yellow fill, a yellow coloring, I did that to remind myself that this is the only cell that I need to manually type a value in every time I do a new question, right? So we're going to set this up so that we could delete this data, put a new set of data in, and then everything will, adjust and recalculate for us, and we'll have a new test result, a new p-value, and we can make our new conclusions and all that kind of stuff without having to kind of redo all of the formulas. But the one thing that's kind of difficult to get a spreadsheet to do is to count just how many columns we have. So it's easier to just manually put in 3. So K is always your number of groups. It's that simple. Okay, let's start off with doing some simple summary statistics. We need to know the sample size and the mean of all of our groups. In this case, the 3 of them. That's easy, right? That's the count function. And then we click on A, and it counts up all the numbers in column A. And then here's the nice thing about having it set up this way, and I'm sorry, I'm just weird about making things centered. If we just grab the corner and drag across, this one is now going to do the count of B, and this would be the count of C. And if we kept dragging, it would then do D, E, and F, but there's nothing in those, right? And we don't need those because we only have 3 columns of data. But the reason why we set it up this way is now if we come along and we have, a fourth, we do another ANOVA example that has 4 groups, we could just come over here and insert a column in between B and C, or really even put one in D, and then just drag this once further to the right, and it'll pick up the same stats for the next column. Well, we could have done this at the same time. We could have also done average for the average of the first column. Again, just clicking on A. And I'm going to do just 4 decimals. We don't need to show so many. And then now if we highlighted both of these and did our dragging technique, it's going to repeat both the count function above and the mean function, right, the average function below. And now we have the number of data values in each of our 3 sets and the average of each of our 3 sets. The next 2 summary statistics we need are capital N, which is the overall sample size, right? So how many data pieces do we have in total? So we're basically just counting up all of our data. A couple different ways we could obviously easily just count up these 3 numbers. We could obviously just type this in by hand, just as like we could have typed these in by hand. But again, we're trying to create something that's generic. So in case we have an example where these are much bigger samples, right? We've got numbers that go way off the bottom of the spreadsheet. We don't want to have to try and count those by hand. So here we could just do equals count, right? The same function, but instead of clicking on just A, you highlight all 3 columns. You'll see that instead of A colon A, it's A colon C. And if you hit enter, there's your 24, which is those 3 numbers summed together. And in fact, rather than wasting time doing this over and over again, I'm just going to do that. Okay. Now, the grand mean should kind of be intuitive. It's just the mean of all of our data, right? So instead of the mean of just the first group and then the second group and the third group, we're now going to do the mean of everything. So this is going to take the average of all of our data. So again, we're going to use the average function. And just like with the count function, we're going to highlight all columns of data. And then that is now the mean of everything. Now, let's give ourselves a couple extra just in case and go, all right, I guess it did come out to an even number. That's just happenstance with this set of data. Obviously, that's pretty rare. Okay, that's step 1. Step 2 is we're going to go ahead and calculate these square deviations for each of our data values. And like I said, it's going to be similar to what we did for standard deviations. We're going to take each number And then we're going to subtract the group mean for that number. So it's going to be 11 minus the 14.22. And we're going to take that difference and we're going to square it. That's it. That's all we're doing, is coming up with those square values. So if we go equals, parentheses, click on that because we want the value in A2, minus, we want this mean, right? We don't want to just type in 14.222 because that's a rounded number. We want to keep all of our accuracy as possible, so we're going to use a cell reference. And then caret 2 squares that. Now, I'll take care of my centering, and I will make this 4 decimals as well, because we really don't need to show the numbers at all. We're not going to use these. It's not like we're going to write these numbers down somewhere or report them. We just need them for further calculations. But in any case, if I then grabbed this and drug it down to repeat the process, it looks like it worked, but it doesn't, because look at the next number. It's A3, which is 14, but minus I4. So it came over here and it subtracted 24 from it and then squared it. And then the next one is subtracting I5 from it and squaring. And then this one is subtracting I7 from it, which is empty, and squaring. That's not what I want, right? Those all have to subtract the same number from it, this number that is in I3. We need to hold I3 constant. And to do that in Excel, it's simple. All you do is put a dollar sign in front of the thing that you want to hold constant. So now this tells Excel, when I drag this function to repeat this pattern, you can let everything change except for the 3. So now when I drag it down, you'll see that everything's quite different. And if I just click on one of them, you'll see that this is now A6, which is this number, but it's still subtracting I3. Right? Still subtracting its group mean from it, and it's being squared. And you might be asking, okay, well, I wanted to keep I3 constant for all those, so why didn't I just put a dollar sign in front of I? Well, then it would have held the column the same, but not the number. So the number still would have changed. It would have gone from 3 to 4 to 5. Right? So the dollar sign is in front of the thing that's being held constant. It's either holding the row constant or it's holding the column constant. And we only wanted the row held constant. Now, the reason why we don't have to worry about the column being held constant is because now if I grab this and drag this across, it's going to do all of these for me instantly. Because the only thing that's being held constant in the formula is the 3, the row 3. So for instance, if we look at this cell, it's now taking B2, right? Because I've moved over. So instead of my results being in D, they're in column E. And so when I was in column D, it was basically telling Excel, hey, take the number that's 3 places to the left, A2, right? I'll click on this one again, right? So it's saying, take the one 3 places to the left and subtract this number that is down and over here and then square it. When I do this, 3 places to the left is now this one, which is what I want. And then it goes down and over, but it goes over, right, the same number of spaces. So instead of stopping here, it stops at J. And then when we go here, it goes 3 spaces left, grabs this number, and then it subtracts the number that's down and over this far, and it grabs this one. And then by the dollar sign in front of the 3, it keeps that constant when we drag it down, and thus we get all of our, squares, our deviation square scores, quickly and easily. I know some of you are going, that's not so easy. Well, if you play around with your spreadsheet, this kind of dragging and kind of what they call filling in a pattern becomes pretty easy. Okay, so that was the next step. We got our squares. The next thing we have to do is calculate these values for each of the 3 groups. And again, it might seem complex, but it's a pretty basic formula. It's really hard to write the proper symbols in this cell. This isn't obviously what we're doing. We're not taking x and subtracting x from it, right? The formula itself is a little different. In reality, or you know, to be more precise, this is what we're calculating. Okay, so little x just stands for each individual number. What these letters should actually look like is this. I'll make it a little bigger. See everything? Okay, where n sub I is just the sample size of each of our groups, right? So in this case, we're going to do this 3 times for 3 groups. So I is going to go from 1 to 2 to 3. So when we're doing n sub 1, that's 9, right? That's the number of things in the first group. And then n sub 2 is going to be 7, and n sub 3 is going to be 8. And for that first time around, when we're calculating this first one, this is going to be 9, and then x bar I is x bar 1. It's the mean of that first group. So that's going to be 14.2222. Then we're going to subtract x bar GM, i.e. the grand mean of everything. So that's just going to be 15 every time, and then we're going to square it, right? And then when we go to this cell, it's going to be 7 times this number minus 15 squared, and then so on and so forth. So if we define the first one, we can drag it across and repeat the pattern. So it's going to equal, right? We need the sample size times, so asterisk, and then we need to do our parentheses. We're going to have our sample mean minus the grand mean and caret 2 to square that thing. Now, just like before, if I drag this across, it looks like it works, but it doesn't because everything changes, right? So when I move over here, it takes J2, which is that sample size, perfect, times, and then in parentheses, it takes J3, which is its mean, but it subtracts J5 from it instead of I5 because the pattern is always move, move, move with where we go. And for this number, to our spreadsheet, I5 isn't I5. I5 is just the cell above me. So when I move over here, it takes the cell above it, which is empty. So just like before, we need to keep that cell constant, and we're moving from left to right. The row stays the same. We don't move from row 5 to anything else when we're taking the mean, but we need to keep the column the same. So that's why we put a $sign in front of the I this time. And then if we drag it across, there we finally get the correct answers for our sums. It's technically the sum of squares, what's called between. Sum of squares between our groups. Okay, let's move on to our next step. All right, so that's the square deviations called between the groups. And then now we need to do the sum of squares within the groups. So we're basically just going to very simply sum up all of these square deviations for each of the groups. So if we simply just do equals sum of this column, and then get this out of my way, drag this across. Those are the 3 sum of squares for each group called within. Okay, so far so good, right? Not too difficult, just some repetitive work to get all of these repeat calculations. Okay, then the kind of the final thing to do is to create our ANOVA table and fill it in with all the correct details. And then calculate our p-value. So this is what our ANOVA table should look like roughly. We want to recreate. Okay, so here is a simple little ANOVA table that I just created here in my spreadsheet. And these are the values that are going to go into each of those squares. You don't have to recreate these letters and all that kind of stuff. And you really don't have to know what they all mean. It's, in fact, all we care about is the F statistic. That's going to be our test statistic. That's the only thing we're ever really going to report. And then we're going to use that to calculate our p-value. But it's kind of nice to fill all this in because you can see the pattern, of like what the numbers are, where they come from, and then how each thing is calculated. That we have these sums of squares, and then we divide that by our degrees of freedom. We kind of get an average, right? We get a mean because it's a sum of a bunch of stuff, divide by pretty much how many things we have, right? Degrees of freedom is almost what we have, but minus one. And then sum up a bunch of other things, divide by its degree of freedom. There's another kind of average. And then the test statistic was called an F because it lives on the F curve, which is very, very similar to the chi-square distribution. It's a bell curve that's been pushed to the left towards the y-axis, and it has a big skewed tail to the right. So it ranges from 0 out to positive infinity. And the closer f gets to 0, then the bigger the p-value is, i.e. the less likely you are to reject the null, right? Because the null is they are all the same. And if they are all the same, then you're not going to get a big difference in these deviations. Thus, your sum of squares are going to be small. And then when you take a ratio of them, f is going to be small. So as f gets closer and closer to 0, that's what happens when your group means are closer and closer to each other. And then the more different they get, right? So the more variation you have in those group means, the bigger f is going to get. So the further you go out to the right, you get out into that little tiny tail, and you get those really, really small p-values, and that's when you reject the null that they are all the same, and you go up. At least one of those group means must be different from the others. So we really only care about the f, but like I said, it's nice to do the others. Okay, pretty easy computations. SS, sum of squares, we're literally just summing up our square sums. And I know there's an SS here and an SS here. I mean, this technically should have been like SSW for sums of squares within each group or something like that. These are different numbers, but we're summing up these square things. So it's just going to equal the sum of, oops, sorry, wrong ones. Between, these are the betweens. So there's my sum of squares between, and then if I just take this and drag down, because of the pattern, there's my sum of squares within, right? That's just summing up I7 through K7, this row of stuff. Okay, degrees of freedom. Well, you can see it's K minus 1, so that's just going to equal this number minus 1. This is N minus K, so it's going to equal N minus K. And yes, I know we could do those kinds of things very easily, by hand. We could count those things up. The mean square is just, we take each of these squares and divide by their degree of freedom. So it's going to equal this number divided by this number. And if I take that and drag that one down, it repeats that process. Down at the bottom, these totals, which again, we don't really need, but we can do them very easily. We're just summing up those two numbers. And the nice thing about Google Sheets, what I'm working in, and oftentimes Excel does the same thing, is it kind of intuitively knows what you want, or thinks it knows what you want. So it's going to, hey, if you're doing a sum here, you probably just want to add up the two numbers that are above it, right? And you go, yeah, thanks. That's exactly what I wanted. And then if I drag this across, it will also sum up these. Now there's never any decimals for degrees of freedom because it's always a whole number. It's a count, so we can get rid of those decimal places. Okay, we don't sum up the mean squares. We just don't. But our final computation, our F statistic, is very easily just the ratio of these two things. So it's just going to equal this number divided by that number, and there is our F value. I just noticed that these numbers don't seem right. And it's because over here, look what I forgot. This group stopped with only 7 pieces of data, but I continued the pattern down too far. I have those 2 numbers that aren't actually part of my data. And same thing with that one. That one shouldn't be there, right? The number of squares should be the same as the number of data values for both of those. So maybe some of you noticed that before and were screaming at your computer that there was a problem. But there it is. I picked it up. Okay, so now everything is accurate. We have our F statistic. So if we're asked to calculate our test statistic, that's our F value here. So a little less than 5. And then our P value is pretty easy to get. We're going to use the f.distribution.right function. So equals f.distribution, and you can see it comes down here, right tail, because we're always doing a right-tailed test for F distributions. Like I said, it's skewed to the right. It goes from 0 out to infinity. We're always looking for the area in the tail because we're always looking for the probability of being, in this case, almost 5 steps away from 0 or more, right? So being further out in the curve. So we're always looking for stuff to the right. The first number it wants, and I'll click on this, so we'll bring it back up. It wants X, which is kind of misleading when they do this in their formula descriptions. X just means the value of your test statistics. So it wants this. So I'm going to click there. Then, comma, the next thing it wants is degree of freedom 1 and degree of freedom 2, which one's 1, which one's 2? Well, the reason why we set up our table this way is it reminds us, we just look at it from things top to bottom. So degree of freedom 1 is this one, comma, degree of freedom 2 is the one underneath it. So it's basically degrees of freedom of the top of the fraction and then the bottom of the fraction, because you remember F is literally just this fraction, right? It's 152.5704 divided by 30.7076. Okay, so here is my p-value. Let me get a little less decimals so we can actually see it. And there it is, almost 2%. So in regards to this question that we were doing that was asking for us to do it at a 1% alpha level, you can see here's the same results, 4.968 when we round to 3 and 0.171. We would fail to reject at the 1% level because this is bigger than 1%, but we would reject the null and say that there is a statistically significant difference between the means at even the 2% level. So that just points out, again, and we've seen this over and over again in my videos, that it's kind of why people say you can lie with statistics, because this data could be interpreted as being statistically significant, and we'd say, yes, there is a difference between these means, or it could be interpreted as, no, there isn't. And it just depends on what level of accuracy you're looking for. Remember, the alpha level that we set is our error rate. It's the chances of making a type 1 error where we reject the null when we shouldn't. So at alpha of 1 means there's only a 1% chance that we can come to the conclusion that there is a difference in one of the group means when in fact there really isn't a difference. Now let's think about it in the context of this question. We're looking at 3 different ways to treat an illness, in this case pneumonia. If we find a difference, or if we think we find a difference, that's basically going to dictate how the hospital operates moving forward. Because if we find out that one of these treatments has a different mean recovery time than the others, then wouldn't it make sense to treat all of our patients with that protocol? And if we look up here, we can see that obviously group 2, the overnight stay, is the most successful one, i.e. they recover in an average of a little less than 11 days, whereas the ones that are just seen for a few hours and then released take 14 days to recover, and the ones that are just sent home with some medicine take almost 20 days to recover. Well, if we reject the null and say that there is a difference when in fact there really wasn't, meaning that yes, we found a difference in these numbers, but there's a 1.7% chance that there really isn't a difference, and these numbers just came up with different values by pure random chance, right? The sample from our population came up with a random chance of having a difference, even though they're not different in the population. So what I mean is if we looked at the entire population of patients who stayed for a few hours versus overnight versus sent home, those three populations would have roughly the exact same mean, but we just happened to take some random samples that had different values, and it looks like those three populations are actually different. If the null were true, right, if they were all the same, then those three populations would be the same, and then this would only happen 1.7%, right, of the time. So that's why we're thinking, okay, then it's probably more likely that they are different, that the populations are different, and each of the three treatments does have an effect. To make that type 1 error, it's not very risky, right? Because if we're wrong and we go, yeah, there is a difference. So if we set our alpha to be 2% or 5% or anything above 1.7, then we're going to reject the null and go, this data is telling us that there's a difference in these groups. And then we could do further analysis to figure out which group is really different from the others. It's pretty obvious that the overnight group is the one that's different from the others. And in fact, the overnight group is definitely far enough away from the sent home group that we're going to see that difference. It might also be far enough away from the few hours group to see a difference. And conversely, the few hours group might be different enough from the sent home group. We just see it that there's a range between all three. And then we would do further analysis to see which one is really different. Because if we found out that the only one that's really different, statistically different, is the sent home group, that the other two being 14 and 10.7 are roughly the same, then as a hospital administrator, we could go, well, then what we really need to do is just stop sending people home with medicine. Because if we get rid of that group, we get rid of the 19.6, we get just 14.2 and 10.7, and those two are roughly the same, right? They're close enough that our p-value would be bigger, and we would say there's no statistical difference between those two groups. And then we could feel safe in having some patients stay overnight and other patients only stay for a couple hours. You know, we leave it up to the nurses and doctors to figure out which one is which. But in the other direction, if we find out that the only statistical differences between the overnight group and the other two, that 14.2 and 19.6 are close enough together, then we're like, well, then, having someone stay for a few hours versus sending them home is no different. The only difference we're getting is if people stay overnight. So then, your protocol would be, okay, if people are really sick, they're going to stay overnight. And if they're not, we're just going to send them home, because it doesn't behoove us to spend the money to keep them for a few hours, right? And have the nurses and the doctors look after them for a few hours, which costs a lot of money, when we could just give them some medicine and send them home. And there's really no difference between how long they're going to take to get better. So that's where, you have to think about what's more important, making a type 1 or a type 2 error, and go from there, set your alpha accordingly. But in any case, a lot of time spent describing an ANOVA test, which you should have hopefully learned in one of my other videos. In this case, all we're doing is figuring out how to calculate this darn thing in our spreadsheets. Unfortunately, there are no easy functions. We can't type in an equal F test, and it just will test the raw data. There are more advanced analytical tools that you could load into your spreadsheet of choice, whether it's Google Sheets or Excel. And then it will do this test for you. All you have to do is put the data in. So basically you would just have to put in columns A through C, and then it'll calculate everything for you. And in fact, it'll spit out this table of results along with a bunch of other stuff. But that's all well and good if you want to use those. I still think it's better to do this thing quote unquote by hand, right? We're really still not doing anything by hand. We're just setting up our spreadsheets to do these kind of intermediate calculations and then calculate everything the way we would with paper and pencil and just an old school calculator if we didn't have these really fancy spreadsheets. Because I think you understand a little bit better what the F score is, right? Where it comes from. We're getting all of these deviation scores. They're kind of like standard deviations, right? How far do our data values deviate from the mean, right? That's part of the formula for a standard deviation. That's why these are called deviation scores. And then we're calculating kind of the sum of all those deviations within each group, and then we're summing up the deviations in between the groups, and then our F statistic is a ratio of those averages, right? The average deviation between the groups divided by the average deviation within the groups. So basically, how much do each of the groups deviate from each other in comparison to how much they just deviate to themselves, right? Because if a group has a large standard deviation within itself, it's going to have a large standard deviation when you compare it to some other group. So that's why we can't just go, well, how deviant are the three groups from each other? Because they might have a really big deviation within themselves. So we have to do this ratio of how much they deviate between the groups, right? And so the difference between each group deviation divided by how much it's deviating within each group. So we're getting this ratio of kind of total deviation divided by individual deviations of groups. And that's what our F statistic is giving us. And the bigger that difference is, the bigger that ratio is, the more extreme it goes out in the tail of our curve, and thus the smaller p-value, and thus the more likely we are to reject that null hypothesis that all of the groups are the same, i.e. have the same mean. Okay, so I hope this helps. This is, if you then have to come back and do an example that has 4 sets, again, what I said is all you got to do is insert a column here to have a 4th set of data, come over here, insert a column there to have a 4th column of squares, highlight your pattern and drag it across so that this column will calculate the squares for the new column of data. Come over here and basically highlight all of this and drag these across, and then it'll just do all of these computations for the 4th group. But don't forget, you're also going to have to adjust your total number, because this is only counting up columns A through C, and your mean, because it's only doing A through C. So you'd have to like re-highlight A through D. If you really want to be fancy and you want to avoid having to do any of those things, if you insert columns in the middle, right? So if you put a column anywhere between A and C, and then a corresponding column between D and F, so that everything mirrors, so that these 4 columns are the same as those 4 columns, and then drag everything across to create your 4th one. These 2 will actually update automatically because it's counting up everything from A to C. If I slip a column in between those, it'll still go from this column of data to this column of data, but instead of being C, it will now become column D. So for instance, if I click on here and do Alt-I for insert, and I do a column to the left, you see how this is now column D? And if I come over here and look at my grand mean, do you see how now it's summing up from A to D? So that, and then of course I would have to come over here and I would have to insert a column to the left of this one so that everything would match, right? So that this column is, it's basically 4 over from that one. This one is 4 over from that one. There's now this new one that's 4 over from this one. And then these scores are 4 over from this one. You'll notice that the numbers haven't changed because when you insert a column like that, it's smart enough to know that it wants to retain its relativity, that these numbers are based on this column and not the one where the numbers used to be. Okay, so that's just some more advice on how you can make these calculators a bit more robust, right? They can do, now you could do something that had 4 groups of data, or 5 or 6 or 7 or 8 or 9 or 10 or 20. Just keep putting more columns in the middle of them so that these two measurements will update automatically, and then just drag this. Well, you'd have to obviously insert some columns. So you're not dragging it on top of this thing, and then just repeat the pattern. Okay, that's everything. Good luck.